In this video, I'm going to derive some very useful vector identities involving the gradient, divergence, and curl. I will be using a shorthand notation for all of the partial derivatives. And you can see that shorthand notation in green over here. So every time I differentiate with respect to x, y, or z, I'm going to use this compact notation. And every time you see this little combination with the partial d and two subscripts, that actually denotes a mixed second order partial derivative. So the order is important over here. As we can see, x is on the left and y is on the right. So we will be differentiating with respect to y first and then with respect to x. That is what this notation means. And you can substitute in any combination of x, y, or z over here. So now that we have this shorthand notation, we can express the definitions of all of these important operators. Let's have a look at the gradient first. So the gradient is up here. The gradient of some scalar field phi is actually equal to all of this over here. So we can see I hat, j hat, and k hat are helping us denote the x, y, and z components. So the x component is the partial derivative with respect to x of the scalar field. And it's the same for the y and the z components. This is how we're going to define the gradient operator. And we're using Cartesian coordinates over here. So everything is in Cartesian coordinates. That's why we have x, y, and z. So if you have a scalar field, you can apply this gradient operator and it will give you a vector. So this over here is a vector quantity and phi is a scalar quantity. So there's no direction in phi. Phi is just a number at every point in space and time. But these guys over here, these guys are the three spatial components of a vector quantity. So this upside down triangle is sometimes called del and sometimes it's called nabla. So this guy is the del operator. And when we write it next to the scalar field, it denotes the gradient. And you can see the same symbol is used down over here. This is the divergence. And the divergence doesn't just have the del operator next to some scalar field. Instead, it has the dot product with some vector field. So here is the difference. Phi is a scalar field, but A is a vector field. So that's why I've written an arrow above to denote that it is a vector quantity. When this is printed or written in textbooks or in web page articles, you will actually see this to be bolded sometimes. But it's very difficult to write in bold. So that's why we, when we're handwriting it, we usually put some sign over it. So sometimes there's a tilde underneath, sometimes there's a bar above, but I'm using the convention that an arrow above makes it a vector quantity. So that's just to distinguish this from a scalar quantity. And A over here, because it's a vector quantity, has three components. It has the x, y, and z components. And when we take the dot product with this del operator, what we're essentially doing is we're differentiating each of those components and adding them together. So the divergence of some vector field A is the partial derivative with respect to x of the x component of A plus the same for the y and z components. So you can see there is some pattern over here, except the main difference is we're taking a scalar input over here and we're getting out a vector, but over here we're taking in a vector and we're using this dot product to give us a scalar. So the divergence gives us a scalar. What about this last term over here? We again see the nabla symbol, or the del operator, but now we're taking the curl of this quantity over here. We're taking the curl with this del operator. And that's giving us this complicated combination. But again, it is actually spitting out a vector quantity. So taking the curl actually gives us a vector quantity. It's not like the divergence. So we can see that we have an x component, a y component, and a z component. And they're multiplying I hat, j hat, and k hat. Those are the unit vectors, and they form an orthonormal basis for the three-dimensional Euclidean space. So you can use the right-hand rule, and you can that can actually help you visualize what this looks like in 3 dimensions. Let's have a closer look at each of these components. This component over here is the x component, but we do not see any x subscript over here. We can find the same pattern for both the y and z components. The x component does not have any x's, the y component does not have any y's, and the z component does not have any z's. So that is a very important property of this definition. So sometimes people like to write a 3 by 3 matrix with ijk at the top and then a row of partial derivatives and a row of ax, ay, and az. Those are the components of the vector quantity. So then if you take the determinant of that 3 by 3 matrix, you will actually get this. This will be the result of the determinant of the 3 by 3 matrix. So that is a very useful memory trick. But I can show you another memory trick that will help you remember what this has to be. So each of these guys have to have no x component for the x guy, and no y component for the y guy, and no z component for the z guy. So you will not see the associated subscript for the associated component. That is what we just discussed. So that is one way to remember. If you're dealing with the x component, you only have y's and z's. So the other point that you always have to remember is which order is it? For this guy and this guy, the order is alphabetical for this first guy. So here you have y and then z, that's alphabetical order. And over here you have x and y. Again, we have alphabetical order. And then we just subtract the swapped over version. What about this middle term? The y component is actually the opposite. Because if you remember, when you take the determinant of a 3 by 3 matrix, there's actually a minus sign that gets introduced for this middle term. And this minus sign just swaps the order of these two guys over here. So if we have a minus multiplying this subtraction, it's just going to swap these guys around. So you can see that x and z, those guys are in alphabetical order. But z and x, those guys are in the opposite of the alphabetical order. So that's a good way of remembering these combinations. Another useful trick is to just find the determinant of that 3 by 3 matrix. These combinations show up a lot in physics. That's why they're very useful. So now what we're going to do is we're actually going to take some combinations of these guys. So we're going to, the first combination that we're going to take is the curl of the gradient of some scalar field phi. So I'm going to take the curl of the gradient of a scalar field phi. And what I'm going to show is that this is always going to be 0. And we're actually going to use that in later videos in this electromagnetism playlist. So this is a very useful property that is fundamental in a lot of the proofs involving electromagnetism. So let's go ahead and actually take this gradient and substitute it into the curl. So we're going to treat this guy as a vector quantity. We're going to pretend that this is our A. So A is actually just going to be replaced by the gradient of phi. So the x component is just this partial derivative with respect to x of phi. And it's the same for the y component and the z component. So that means if we were to substitute this guy inside of here into this definition, this az would no longer be az, but it would turn into a partial derivative with respect to z of phi. So what we can do is actually we can use this notation over here, this mixed derivative notation. So for this term over here, we're going to have a z derivative acting on phi, and then a y derivative. So what we can do is we can write yz over here, and that's going to denote a z derivative and then a y derivative. So let's do that. So I'll write this out. So first we're going to have a look at this x component. So the x component is going to have dy, and then we're going to have a z. So that's the z derivative, and then we need to have a phi. And from that, we're going to subtract off this guy over here. And that's just going to be swapped over. We're going to have zy. And you might be seeing some interesting pattern over here. So this is going to be the x component. So what have we done? All we've done is we've taken this az and we've set that equal to the z component of this gradient. So then we differentiate with respect to z, and then with respect to y. That's what this denotes over here. So first we have a z derivative acting on phi, and then we have a y derivative. And in this term over here, we have the opposite. We just have to swap these guys around. So now let's do the y component and the z component. So the y component, which we can just read off over here, is going to be the partial derivative, and we're going to have a z and an x. So we'll have z x of phi. We're going to subtract off xz. That's xz, and then we'll have phi. So that is going to be the j component, or the y component. And the j unit vector points in the y direction. And to that, we're just going to add this final z component, and the z component is going to have xy. So we'll differentiate with respect to y first, and then with respect to x. And we're going to have a phi over here. And then we're going to subtract from that yx. So we have dy x of phi. And this is in the z direction, so we have the k unit vector. So what can we see over here? In each of these terms, we just have the swapped over derivatives. So these guys are all mixed derivatives. That's shown in this condensed notation over here. So here we have yz, zy, then zx, xz, and then xy, yx. So what is something that we can do over here? So what do we want? We want to cancel all of these guys. So we need all of these components to be equal to 0. When are they all equal to 0? Well, they're only equal to 0 if differentiation is commutative. If we can swap the order of these derivatives, then we can set all of these guys equal to 0. Are we allowed to do that? In general, you can run into problems if you swap the order of derivatives. But for nice continuous functions, this actually works. You can swap the order of the derivatives. So that means all of these guys are just going to go to 0. This is going to be 0, this is going to be 0, and this is going to be 0. So the x component, the y component, and the z component are all 0, and that means this is equal to 0. So the curl of the gradient of some scalar field is always going to be 0 if you're allowed to swap the order of the derivatives. And in most electromagnetism applications, you're going to be dealing with real-world continuous functions. So this phi is going to be a continuous function which you can differentiate in different orders. So you can swap the derivatives of these nice continuous functions. So that's why this is always going to be 0 for our practical purposes. Now, mathematicians can cook up functions that actually don't allow for this swapping. So this, in general, you have to be careful when you swap the order of the derivatives. So now let's find another interesting vector identity. Let's take the divergence and the curl together. What happens if we take the divergence of the curl? What is that going to look like? So we'll write that underneath. So let's say we have the divergence of the curl of some vector field A. What is that going to be equal to? We're going to show that this is also equal to 0. So if you take the divergence of this curl over here, this guy is going to output a vector. Remember, over here, we also outputted a vector. So we began with a scalar field. We used the gradient to turn that into a vector field, and then we took the curl of that, and that gave us 0. Over here, we're beginning with a vector field. We're using the curl to turn that into another vector field, and then we're going to take the divergence of that, and that's supposed to give us 0. So let's prove that. So if we take this guy as the input, what are our x, y, and z components? So the x, y, and z components of the curl of A are given over here. This is the x component, this is the y component, and this is the z component. So we have to substitute these x, y, and z components into the expression for divergence. So this ax term, this ay term, and this az term, those guys are just going to be all of these guys in the brackets. So let's go ahead and write that out in full. So what we're going to find is that we have to take the x derivative of the x component of the curl. So let's do that. So we can put this in brackets. So what we'll have is dy az minus dz ay, and this is going to be our x component, which we're differentiating with respect to x. Now we have to do that for the y and z components as well. So let's do that for the y and z components. So we're going to differentiate with respect to y, and over here we're going to have zx and then xz. We have z and then x, and then we have x and z. So this is the y component, which we're differentiating with respect to y. And when we're taking the partial derivatives, we're keeping all of the other guys constant. That is actually what the partial derivative is defined as. You have to keep all the other variables constant, and you're only differentiating with respect to the variable of interest. So that is this y component. And now let's have a look at the z component. Well, the z component, which we're going to differentiate with respect to z, is going to be like this. So we'll have x, and then we'll have y, and we'll subtract from that dy ax. So we can see some very interesting patterns. But in this form, we can't easily group things and cancel them out. Over here, we just have to substitute it in, and we can immediately see these corresponding terms. So this was very easy to group together and cancel out. But this takes a little more work. So what we have to do is we have to distribute these derivatives inside the brackets, and that's going to give us a bunch of terms which we will see that we can group together and cancel. So let's do that. So what is this going to be over here? This first term is going to have a mixed derivative. I'm going to use this notation again over here. So I'm going to have dxy of az. I'm going to subtract from that dxz of ay, and that is distributing this x derivative onto each of these terms over here. So here we get an xy acting on az, and here we have an xz acting on a y. So let's do that for these two as well. So here we're going to get plus dyz, so that's y and a z, and that's acting on ax. And then we're going to subtract from that dyx acting on az. So that's this term over here, yz acting on x, and yx acting on z. And finally, this term over here, so what we're going to get is dzx acting on ay. And the final term, which I slightly erased, is going to be zy acting on ax. So you can see that this z and x come together, act on ay, and this z and y come together and act on ax. In all of these terms, you never see a repeated index. All of the indices have one x, one y, and one z, but they're all in different orders. So we can't immediately see that these guys are going to cancel out. So let's reorder everything. So let's group together all of the ax's, the ay's, and the az's. So can you see all of the ax's over here? I can see one ax over here, and I can also see one ax over here. So let's group these guys together. I'm going to group them together and write them underneath. So we're going to have this ax and this ax. So what is a coefficient of this ax over here? Well, we have this partial derivative, and we have a y and a z. So that's going to give us dyz ax, and then we're going to subtract off dzy ax. So that is the first two terms that we just grouped together. Now let's do that for a y and a z. So for a y, I can see one ay over here, and I can also see one ay over here. So this ay is zx. Over here we have a zx, and that's acting on ay. And we're going to subtract from that this term over here, and this term has an xz. So we have xz acting on ay. And finally, we have to add to that the last two terms, which have az's in them. So we can see one az over here, and that az has a derivative with respect to x and y. So that's xy az. And we're going to subtract from that one more, which is right over here. So we can see there's a minus, and we have a y and then an x. So we have y and x acting on az, and we can close the bracket. So what do we see in these three groupings over here? In this first grouping, we can see ax and ax. Here we have the partial derivative with respect to y and z, and here we have z and then y. So these guys are just condensed notations for these mixed derivatives. So again, if we assume that we can swap the order of differentiation, these guys should cancel. These guys should be the same. There shouldn't be any difference if you take the derivative with respect to y and then with respect to z, or if you take the derivative with respect to z and then with respect to y. So what we can find is that given our continuity conditions, this is actually going to be equal to 0, because we have a yz and then a zy, both acting on ax. Over here, we also have a y and a y. Here we have zx and xz, so that's going to give us 0. And finally, over here, we have an xy and then a yx acting on a z, and that's also going to give us 0. So this is equal to 0. So what have we found? We have found two very important vector identities. I'll write them at the bottom. So we have that the curl of the gradient of some scalar field phi is equal to 0. And we also have the fact that the divergence of the curl of some vector field A is equal to 0. So I'll put these guys in a box because they're very important. And they're actually the entire purpose of this video. So now we can see that these guys are always going to be 0. So the curl of the gradient of some scalar field is 0, and the divergence of the curl of some vector field is also equal to 0. We're going to be using this in later videos on electromagnetism. These guys are very, very important vector identities because they allow you to simplify equations, and they also allow you to get some useful properties involving Maxwell's equations and the scalar and vector potential. So always keep in mind, this A over here is a vector potential. So it's actually a vector field, and it has three components. It has an X and a Y and a Z component. So implicitly, whenever you see equations involving this A, you have three implicit equations. You have an X equation, a Y equation, and a Z equation. And if you switch to different coordinate systems that are not Cartesian coordinates, you're still going to have three equations, but they might be a little more complicated, like in cylindrical or spherical coordinates. So we're going to use these two vector identities in the next few videos. Make sure you watch those next few videos. You can find them in the electromagnetism playlist.